Hello, everyone, and welcome to another measurements and instrumentation class. In the previous class, we finished Wheatstone bridge, and for Wheatstone bridge, we have two main applications. Number one is to find an unknown resistance. How can we find an unknown resistance? We would have a variable resistor and two fixed known resistors, and we balance the Wheatstone bridge. And when you balance the Wheatstone bridge, the current passing through the middle arm is going to be 0. Therefore, you can determine an unknown resistance. Another application for Wheatstone bridge was for sensors. So one of the arms, you replace it with the sensors, and we did both of them in the lab. For the first part of the lab, we had multiple resistors with different values, and we had a potentiometer, and we adjusted that, and we balanced the system. We determined the unknown resistor. And part two, we had a photoresistor, and that photoresistor, when you put it in dark or shine a light on it, light source on it, you would see that the middle arm voltage or current would change, and therefore you can use it as a sensor system like a DOS to DON system and so on. Now, we can use the principles that we had for Wheatstone bridge and apply it for a different type of bridge. Another type of bridge that we have is called a shearing bridge. Again, today we're going to start with this shearing bridge, then Maxwell bridge, and different types of shearing and Maxwell bridges. And we would solve some problems as well. Now, a shearing bridge is a type of bridge. It's very similar to Wheatstone bridge, but instead of having 4 resistors and having a resistor in each arm, we replace the resistors in some of the arms with capacitors. And this bridge is specifically used for measurement of an unknown capacitor. Again, one application of these bridges is to measure unknown values of impedance, I could say in general, and using that impedance, you can actually find a capacitor, unknown capacitor, or an unknown inductors. If we want to find a resistor, unknown resistor, we use Wheatstone bridge. For an unknown capacitor, we use shearing bridge. For an unknown inductor, we use the Maxwell bridge. So each of or the Hayes bridge. Now, this graph shows a typical shearing bridge. Again, it's for measurement of an unknown capacitor, and the dissipation factor and measurement of relative permittivity, which are the same. And in this shearing bridge, again, we have 4 arms. C1 is unknown. You can see here. Let me, by the way, pen. So here C1 is unknown, and the value is to be determined with the series electrical resistance R1. So this C1 is our unknown that we want to find, and we are always having this with a resistor in series with it. C2 is a standard capacitor. C4 is the variable capacitor, and R3 is a pure resistor. And all of these, the capacitor, C2, R3, R4, R1, these are all known, but R4 and C4 are variable capacitors and variable resistors. So C4 and R4, everything that we have in this arm, the CD arm, these two are variable. The rest of them are fixed. R3 and C2 are fixed. R1 is known, R3 is known, and C2 is known, and we want to find C1, which is unknown. So R4 is a variable non-inductive resistor connected to in parallel with variable capacitor C4. Now the supply is given to the bridge between the points A and C. From theory of AC bridges we have at balance conditions. And as you remember for a Whitson bridge, do you remember how we figure out it was balanced? What was the equation behind it? If we multiply this arm into this arm, and it was equal to the multiplication of the impedance from this arm to this arm, then we had a balanced bridge. And we wrote it like this. R1, if for example, this was R1, this was R3, this was R2, this was R4. R1, R3 was equal to R2, R4. Am I correct? Now I can expand that. Instead of saying R1, R2, I can say the impedance Z1, Z3 is equal to Z1, Z2 times Z4. So I can say if the impedances of Z1 times Z3 is equal to Z2 times Z4, then we have a balanced system. And when we have a balanced system, the current passing in the middle lane, what would this current be? 0, or the voltage difference would be 0. Now, what is an impedance of a resistor? An impedance of a resistor, I'm going to call it ZR, is equal to what? Resistance, yes. What is the impedance of a capacitor? Yes. Or 1 over j omega c, or negative j over omega c. What is the impedance of an inductor? Just a reminder. J omega L. And how do we measure resistance? It's in ohms, okay? And capacitance and impedances. So we can use this principle, the principle that we had, Z1, Z3 is equal to Z2, Z4, and replace it with the impedances. Now, what is Z1? What is the impedance of Z1 here? Z1 is going to be the combination of R1 plus the impedance of C1. So it's going to be R1 plus 1 over j omega C1. Okay, this would be Z1. And what is Z3? If, for example, this one is Z3, it's going to be R3. And what about Z2? It's going to be 1 over j omega C2. And Z4 is going to be 1 over j omega C4 in parallel with R4. So it's going to be R4 times 1 over j omega C4 over R4 plus 1 over j omega C4. So again, if we rearrange it, substituting the values of Z1, Z2, Z3, and Z4 in the above equation, we get Z1 is going to be R1 plus 1 over j omega C1. And when we put R4 and C4 in parallel, again, you have to find them in parallel. The first one, they were in series, so we just add them. The second one, since they are parallel, it's going to be 1 over Z1, I'm sorry, 1 over ZR plus 1 over ZC, which gives us R4 over 1 plus j omega C4 R4, which is going to be equal to R3 j omega C2 over j omega C2. Why? Because if I multiply this by this, it's going to be R3 times Z2, and Z2 is 1 over j omega C. So it's going to be R3 over 1, j omega C2. Now, if we simplify this equation and equating the real and imaginary parts and separating them, we get R1 is going to be equal to R3 C4 over C2, and C1 is going to be C2 R4 over R3. These are very important equations. So we can find R1 and C1, the unknown capacitor and the unknown resistor. Sometimes R1 is given, most of the time it's not given, it's just unknown. But the rest of the capacitors, the resistors are known. So we can find the unknown resistor and capacitor using these two equations. Now, in a shearing bridge, we usually use high voltage high frequency. Okay. The reason is because these capacitors, first of all, they are very, very sensitive and they have small capacitance. And when you have a small capacitance, you need high voltage to be able to measure it. If you have small voltage, you're going to have leakage, and the portion of error to the measurement is going to be so low that you can't even pick it. So a shearing bridge, one drawback I could say, it's you need high voltage and high frequency to be able to do the measurements and build a shearing bridge. So for the measurement of small capacitance, we need to apply high voltage and high frequency as compared to low voltage, which suffers many disadvantages. As mentioned, you can't measure it. You're going to have a lot of loss in the system. It's very difficult to do the measurement. Another problem with this bridge is that variable capacitors are very difficult to come by. They are not very common. We barely use them. They are expensive and they are not accurate at all. So this is a huge drawback. C4, if you want to find an variable capacitor, again, they are very difficult to build. Why? The reason is if you want to build a variable capacitor, as you know, the capacitor, we have two conductive plates. And what do we have in between? We have an insulator, okay? And what is the capacitance? Relative, if I want to find the capacitance, it's going to be actually relative to the area A, the area of the plates, and epsilon, which is the space or the insulation between them, over D, which is the distance. Obviously, if you have a capacitor, you cannot change the area. You can't change the insulation. The only thing that you can change is what? The distance. Now, the problem is these distances are around 1 millimeter or something less than that. So a very small adjustment is going to have a huge effect. It's very difficult. Even an impact could change the capacitance. That's the reason these capacitors are expensive and very difficult and not very accurate. Now, this slide shows an explanation. By the way, this bridge here is an AC bridge. We have a transformer. The reason that we use this transformer is because this transformer increases the voltage. So you go from 120 volts to 1000 volts or 2000 volts. But the other thing is this works on high voltage, high frequency like 50, 60 hertz, sometimes more. But the current is extremely low because if you have a high current, you're going to have a high power and it's going to blow up. This is very sensitive. So you're going to have a current around few microamps even or milliamps, but the voltage is going to be high. Now, the bridge arms A and B and AD consists of only capacitor as shown. You can read faster than I can. And the way that it works, again, the impedance between AB times the impedance between CD should be equal to the impedance between BC times the impedance between AD. The high voltage supply is usually supported by a transformer. Here it's a 50 hertz. It could be 60 hertz, something like that. The reason this is a 50 hertz because this is like a European, standard, and US will obviously have 60 hertz, and you can just plug it into the outlet and do the measurement. But usually, what we do is we use a signal generator to generate a signal, high frequency signal, so we don't even need this transformer, and you can give that high frequency signal directly to the system. The impedance arms are of AB and AD are very large. Therefore, this circuit draws low current, hence power loss is low. But due to this low current, we need a very sensitive detector to detect this low current. Like 5-10 years ago, they used oscillating galvanometer. Now they use these very accurate digital multimeters to do that. And since R3 and C4, R4 are relatively small, the voltage between BC and DC are also relatively small. So you're going to have a small voltage on the second half at point C. Again, the AB, again, and AC are high impedances, in contrast with BC and DC, which are low impedances. Therefore, the voltage difference between points B and C and D and C are going to be relatively small. And therefore, we need a very accurate and sensitive detector. The fixed standard capacitor C2 has compressed gas, which works as dielectric. Therefore, dissipation factor can be taken as 0 for compressed air. Earth screens are placed between high and low arms of the bridge to prevent error caused due to intercapacitance. So another problem that these have, and we have this in a lot of transistors as well. In high frequency, what happens is like when you have an element like a resistor or transistor, you have the terminals coming out of the transistor or the resistors. These are two conductors. You have air between them, and they act like a capacitor as well. And this is actually very low capacitance. When the frequency goes high enough, this resistor or transistor actually becomes short-circuited because you have a capacitor, small capacitor, and that acts like a high-pass filter. Okay, now, first example, we're going to have a small quiz. Mainly it's because of attendance. I'm going to give you a few minutes to think on the first one. And then the second one is going to be the actual quiz. But if you get the first one correct as well, I'm going to give you bonus points for it. So example number 1, in a sharing bridge, and you can use the slides. A balanced shearing bridge. The standard capacitor C2 is 100 picofarad. A resistor R3 is 500 ohms. And variable resistor R4 is 1000 ohms. We want to find the unknown capacitance C1. I'll give you. If you wrote it down, I can go back to the equation if you want. Let me know if you want me to go back to the equations. Let me copy this. And also find the unknown resistance R1 as well. Did anyone solve it? Okay. What is C1? Yes. And what is R1? Okay. So C1 in a balanced shearing bridge is going to be C2 times R4 over R3, according to this equation. Let me copy the, put it. Yeah. So we're using the second equation. So C1 would be equal to 100 times 1000 over 500, which is going to be 100 times 2, which is 200 picofarad. Now R1 is equal to R3 C4 over C2. R3 is 500, C4 is 250 picofarad, so times 10 to the power of negative 12. And what is C2? C2 is 100 picofarad. So what did you get again? Yes, 1250, which is a very small capacitor. Thank you. Now the quiz. A shearing bridge is balanced with R3 equal to 800 ohms, C4 equal to 0.002 microfarads, and C2 equal to 0.01 microfarad. Find the series resistance R1 of the unknown capacitor. And pretty easy. We want to find R1, which is going to be R3 C4 over C2. Did everyone solve it? So it's going to 800 times 0.002 times 10 to the power of negative 6 over 0.01 times 10 to the power of negative 6. So what is the answer? Okay. Now you're going to have another question after the inductance measurement using Maxwell bridge. Now, another type of bridge that we use that works on the principles of Wheatstone bridge, and actually it's working on the principle of comparison, meaning we could compare an unknown resistor with a known one, and we determine the unknown resistance or impedances. It's called the Maxwell bridge. Maxwell bridge is used to measure self-inductance. We don't want to measure mutual inductance here, so technically it's for measuring inductance. And again, it's on the principles of the Wheatstone bridge that we had, and we have an unknown inductance, and we determine it by comparing it with a known value of or standard value. We have two different types of Maxwell bridges. We have the Maxwell inductance bridge, and we have the Maxwell's inductance capacitance bridge. Again, two different methods for determining the self-inductance, Maxwell's inductance bridge and Maxwell's inductance capacitance bridge. By the way, in the exam, you're going to have at least 3 or 4 questions on these. And questions may be like, what type of bridge is used for measuring inductance? Shearing, Maxwell, Whitson. So you're going to have theory questions also, solving numerical questions as well. Now, this slide is showing a Maxwell bridge. Now, again, because it's the same principle that we had for Maxwell and Whitson bridge, again, these two are inputs and outputs, which are connected to a voltage source. You can see our voltage source E. And if we multiply this arm's impedance by this one, and we multiply this one by this one, if it's balanced, then we should have 0. So if I name this Z1, this is Z4, Z3, and Z2. Z1, Z4 is going to be equal to Z2, Z3, if we have a balanced bridge again. Now, what is the impedance of an inductor, ZL? What is it? J omega L. And what is the impedance of a resistor? Just R, yes. So if I want to find the impedance of the first arm, for example, Z1, can you help me to determine Z1? What is Z1 going to be equal to? It's going to be the impedance of ZR1 plus ZL1. So ZR1 plus ZL1, because they are in series. So it's going to be R1 plus J omega L1. And we can do it the same way for R3, R2 and L2 and R4. So in this configuration, let L1 to be L1 is our unknown inductance of resistance R1. L2 is a variable inductance of fixed resistance R1, I'm sorry. R2 is a variable resistance connected in series with inductor L2, and R3, R4 are known non-inductance resistance. And when we balance them, we use the equation that we had. We reach these two equations. I'm not going to go through the proof. It's pretty simple. But we reach these two equations. L1 is going to be equal to R3 over R4 L2, and R1 is going to be equal to R3 over R4 times R2 plus R2.
So what is the difference in the capital R2 and lowercase r2?
That's a great question. Thank you for bringing that up, and I wanted to explain this. So R2, the lowercase r2, is the internal resistance of the inductance. Okay, inductance itself, it's made out of a conductor, but it's not a perfect conductor. You still have a little bit of resistance. And since R2, the capital R2 is usually, if it's much bigger than the resistance of the inductance, we can neglect that, but sometimes it's significant enough that we have to add that. So technically we're doing R3, R4 times the R2 or the resistance in arm number 2, which is going to be the combination of R2 plus the R2 that we have. The value of the R3 and the R4 resistance varies from 10 to 1,000 ohms. With the help of the resistance box, sometimes for balancing the bridge, the additional resistance is also inserted into the circuit. Now, another type of Maxwell bridge is called the Maxwell's inductance capacitance bridge. in this, the unknown resistance is measured with the help of or better to say, the unknown impedance is measured with the help of the standard variable capacitance. The connection diagram of the Maxwell bridge is shown in the figure below. Again, if Maxwell inductance capacitance bridge is very similar to shearing bridge, but shearing bridge doesn't have an inductor. It just has R1. This one has an inductor. So keep in mind, if you see an inductor, it's a Maxwell bridge. Shearing bridge only has resistance and capacitance. So difference between this and a shearing bridge is that in a shearing bridge, you don't have this L1, but in a Maxwell bridge, you have it. Now again, same principle, this impedance times this is equal to this. So R1 or Z1, Z4 is equal to Z2, Z3 again. But now here Z4 is 1 over J omega C4. By the way, this is Z4 in parallel with R4. Now, if we simplify that, again, L1 is unknown inductance of a resistance R1. R1 is variable inductance of a fixed resistance R1. R2, R3, R4 are variable resistance connected in series with inductor L2. And C4 is a known non-inductance resistance for balanced conditions. Now, again, because we have the capacitor, we add that, and by separating, again, the imaginary and real part, we get to this equation. R1 would be R2, R3 over R4, and L1 would be R2, R3 times C4. The above equation shows that the bridge have two variables, R4 and C4, which appear in one of the two equations, and hence both equations are independent. Now, the problem with the shearing and the Maxwell bridge is that these are very sensitive bridges. Again, building a variable capacitance or a variable inductance is a very difficult challenge. Therefore, and we need high voltages usually, and it's sometimes it gets very, very tricky. But there are advantages and disadvantages of this system as well. Now, for a Maxwell bridge, the advantage is that the balance equation of the circuit is free from frequency. Why? Because again, these cancel each other out. So you can see that omegas are canceling each other out, and you're left with no omegas. In other words, they are independent from frequency. Now, both the balance equations are independent of each other. The Maxwell inductor capacitors bridge is used for measurement of the high range inductances. But again, having a variable capacitor is very expensive, very rare. I had students working on it last semester, and it took them 3 months to find a variable capacitor. And when they got it, it wasn't even the one that. So the data sheet was completely different. They wanted to build a walkie-talkie, and they needed a variable capacitor, so they couldn't. Though the older generation, there was analog ones, they had variable capacitors to set up the RLC and the antenna and so on. And that was a large one. So imagine a small one, it's going to be very difficult. The Maxwell's inductor capacitance bridge requires a variable capacitor, which is very expensive. Thus, sometimes the standard variable capacitor is used in the bridge. So instead of having a variable capacitor, you just have different capacitors and you just replace them. Same thing that you had in your lab, replacing different resistors. You could have used a potentiometer, or you can use the 10 ohm, 20 kilo ohm, 10 ohm. And you can do the same with the capacitors. Just take them out and replace them. The variable capacitors are expensive, hard to come by, but the fixed ones, you just have different values of fixed ones. So you have from 1, picofarad to 100, millifarad, something like that. And you could just, but you need a lot of resistance, capacitors, and you need to take them out. It's going to be a challenge. Now, the bridge is only used for the measurement of medium quality coils. Because of the following disadvantages, the Hayes bridge is sometimes used for the measurement of small circuits, inductance, circuit inductance, which is the advanced form of the Maxwell bridge. You add a couple of capacitors and inductors, but you make it much more complicated, but you can measure it more accurately. Now, let's go to example number 2 and quiz number 2. At balance in a Maxwell's inductance bridge, the standard inductance L2 is 400, R3 is 300 ohms, and R4 is 600 ohms. Find the unknown inductance L1. Okay, now I'll give you 5 minutes. Then I would solve it. Okay. Did you find it? What is the answer? Yes. Let's go back to the equation. I don't know why I can't move it. Doesn't allow me to move it. Interesting. Okay, anyway, I'm just going to leave it here. So we're going to use the equation that we had. We have R3, R4 are known, and we have C4 known as well. And what is the other equation that we had?
They use the one for just the inductance bridge, L1 is equal to R3.
Yes. I think it's here. Yes. It's going to be this one. I'm sorry. Yeah. This is for the inductance capacitance bridge. So L1 is going to be equal to L2 R3 over R4, which is equal to 4 times 300 over 600, or 4 times 0.5, which is 200. Thank you. So this is L1. Now, next question. A Maxwell's inductance bridge is balanced with R3 equal to 400, R4 equal to 200, and R2 equal to 50 ohms. Coil resistance of standard inductor R2 is 10 ohms. Find the unknown resistance R1. So here, the ratio between the internal resistance of the coil resistance of the inductor to the resistance is 1 to 5. So you can't ignore it. But if, for example, this was 1 and that was 50, then you can neglect it, and that's going to make a huge difference. But here you can see since R2 is also small, it's going to be significant compared to R2. So you need to put that into account.
What's the like bottom ratio you would use for?
1 to 100, yeah. And you're going to barely find that. If it's going to be that, the other arm is going to be significantly smaller, and it's very difficult to measure the voltages in a very, very sensitive galvanometer or DMM. So if I want to find R1, according to the equation that we have, it's going to be R3 over R4 times R2 plus R2. Now R1 is going to be equal to 400 over 200 times 50 plus 10, which is 2 times 60, which is 120 ohms. Now let's solve one from the inductance capacitance. So given R2 is 200 ohms, R3 is 300 ohms, and C4 is 2 microfarad. We want to find L1. think all of you have already solved it. So using this equation, L1 is equal to R2, R3 times C4. L1 is equal to R2, R3 times C4 for the inductance capacitance bridge. So L1 would be equal to 200 times 300 times 2 times 10 to the power of negative 6. So it's going to be 6,000 times 2 times 10 to the power of negative 6. Or in other words, it's going to be 0.12 Henry. Or 120 milliamp. Okay. That's it for today. On Thursday, we're going to start with contactors. Keep an eye for a very important announcement about next week in the upcoming exam. We're going to have a review session for the upcoming exam and so on. But this Thursday, we will finish with contactors. And again, next week, we're going to have a review session on the exam and so on. Please bring your quiz and put it here. Thank you so much and have a great day.
What was that?